All right, so moving right along, we just finished up 15.1. So 15.2 is an example. If you are in the classical class, you should do it entirely on your own. And in the algebra-based class, make sure you understand the steps. I don't expect you to do the integral, but I do want you to see how the sum is set up and how to reason through something. All right, so moving on to 15.3, we're going to do another derivation. So this time we are going to do a uniformly charged thin ring. And again, this is just, we want to practice how to think through this because this is going to be a repeat that we're going to see over and over and over again, not just for electric fields, but for magnetic fields, and eventually when we get to flux and setting up Maxwell's equations. Way fun. Okay, so we have a uniformly charged thin ring. It has radius of capital R and charge lowercase q. All right, so to go after the electric field from this ring, so we want this, we need to divide and conquer. So we want to start breaking it up into small pieces. So we've got our ring here, and we'll start there, and then we're going to go around and just add it up. So if we have these little slices, what we can see here is it's going to vary by theta. So all of these slices will have angular length delta theta. And in this case, so we said it's a thin ring, so what we are assuming is a point charge addition. So we're going to be summing together all these little point charges. Okay, so step 2, we want the contribution of one piece to the electric field. So here's where we set up our axis system. So let's go ahead and do that here. And we will be working in 3 dimensions. So we're going to put x here, y here, and we're going to be observing the electric field at some point along the z-axis, which goes right through the ring. So each of these little slices that we set up, these little delta thetas, our r vector will point from our observation location in z to the little delta theta on the ring, and then we're going to set the origin at the middle of the ring. All right, so here is our axis setup, and now let's write a few things down. Actually, I'll leave this picture here so we can easily reference it. All right, so the location of each piece varies by theta, which is a hint that that's going to be our summation variable. And theta will equal 0 at the x-axis. So we can see that in the way that we drew our picture. All right, so we can already identify the summation variable. Let's write that down. This is just a way that we can check ourselves. And so our r vector is going to be our observation location in z minus the source, which will vary in theta. So we are in z, so this is 0, 0, and I drew this so it was coming out, so that would be positive z minus r cosine theta, r sine theta, and 0. And this, of course, comes from looking at the trigonometry. So r is going to be the hypotenuse of the triangle. And if we look at both of these, so SOHCAHTOA be opposite over hypotenuse. So in this case, theta, in this case, that r here would cancel out the r on the bottom, giving us just x or y. Okay. So this is equal to minus r cosine theta minus r sine theta z. The magnitude of r is equal to the square root of minus r cosine theta squared plus minus r sine theta squared plus z squared. We're done with that picture for now. And if we use the trig identity that sine squared sine squared plus cosine squared is equal to 1, this becomes r squared plus z squared to the power of 1/2. R hat is equal to the r vector divided by the magnitude, which is equal to minus r cosine theta minus r sine theta and z divided by r squared plus z squared to the power of 1/2. And as we've already said, this is a thin ring, so we're going to use the electric field equation for a point charge, which is equal to 1 over 4 pi epsilon naught q over r squared times r hat. In this case, q is going to be the delta q of each of the little charges. So then our electric field for one piece is equal to 1 over 4 pi epsilon naught delta q over, we'll plug in our expression for r into the bottom, r squared plus z squared. And again, we're just looking at the scalar component, because then of course we would multiply this by the vectors. And it's a good idea to go ahead and write this out first and then to expand it out into a vector. It's just, there's a lot of steps to keep track of. So it's worth the time to do just a touch more work to make sure that you're keeping track of all your variables. So as we know, this is the scalar component delta E times r hat. And so delta E is equal to 1 over 4 pi epsilon naught q times delta theta over 2 pi, because there's 2 pi radians if you go around the circle, divided by r squared plus z squared times minus r cosine theta minus r sine theta z over r squared plus z squared to the power of 1/2. Okay, so let's go ahead and simplify this out just a little bit. So delta E is equal to 1 over 4 pi epsilon naught, and do take the time to simplify out these expressions. This is really messy, so it's good to write it out completely once and then simplify. And in terms of my grading, the more steps you give me, if something goes wrong, the easier it is for me to figure out what happened. All right, so this is a much nicer way of looking at this. So we've basically combined these two expressions to get the 3/2, and we've neatened up that numerator over there. Okay, so we now want to think about what components of the equations are going to be non-zero. So for that, let's go ahead and look at our picture again. Okay, so if we look at this picture, we can see that for every x, there's going to be a negative x, and for every y, there's going to be a negative y. So we're going to have 0 in the x and y components. So the only non-zero component is going to be in z. This is why drawing pictures is so important. So it would be sufficient to say based on picture, x and y are 0. Only z is non-zero. All right, so then we can just look at delta Ez. Now you would need this statement here. You need to justify if you're only going to give me delta Ez. If you want to derive this numerically instead of pictorially, you're welcome to do that. It's more work, but you know, you do you. So this is equal to 1 over 4 pi epsilon naught q over 2 pi z from this right here over r squared plus z squared to the 3/2 times delta theta. So we've brought this delta theta out because this is our summation variable, so it's just making it so that we can set up that integral a little bit easier. So dEz is equal to 1 over 4 pi epsilon naught q over 2 pi z over r squared plus z squared to the 3/2 d theta. And by the way, general, you would just need to stop here. This is your expression, you're done. Then you can just jump right to the solution. All right, classical, we are not done. So E sub z is going to be the integral from 0 to 2 pi as we go all the way around the circle of dEz, which is the integral from 0 to 2 pi 1 over 4 pi epsilon naught q over 2 pi z over r squared plus z squared to the power of 3/2, and we're going to be integrating, summing by d theta. Now all the constants can go in front, so you can see everything that does not depend on theta. So that doesn't depend on theta, that doesn't depend on theta, that doesn't depend on theta. We just have this here, so we're just going to integrate d theta. Nice, easy integral. So I'll go ahead and write that out explicitly. 1 over 4 pi epsilon naught q over 2 pi z r squared plus z squared to the power of 3/2 0 to 2 pi d theta. All right, so then I'm going to look at just this. So this then is just theta solved from 0 to 2 pi, which is equal to 2 pi. And we can see here that there's a 2 pi now on top and a 2 pi on bottom, so these two will cancel. And so we get Ez, which is equal to 1 over 4 pi epsilon naught qz over r squared plus z squared to the power of 3/2. Okay, so now we have our expression for a ring. So step 4, let's just check those units. So already we have just a z, which we predicted from our picture, and then the units, we would have Newton meters squared over Coulomb squared times Coulomb meters over meters squared to the power of 3/2. And this gives us newtons per Coulomb. So you can see that this cancels that. And then there you go. All set. Okay. So let's look at some special cases for the ring. So at the center of the ring, z equals 0. So if z equals 0, let's see, if we look at this equation here, where's our z's? We're going to have a 0 here and a 0 here, and now we're multiplying the whole thing by 0. So at the center of the ring, z equals 0, and therefore the electric field is 0. No electric field at the center. Okay, that's easy. Let's look at another special case. Z is much, much larger than R. So now we're very far away from the ring. So we have R squared plus Z squared to to the power of 3/2 is approximately, this now becomes negligible, so then we've got z squared to the power of 3/2, which is z cubed, and so the electric field then is proportional to z over z cubed. Everything else is a constant, which is the 1 over z squared dependence, which basically means the ring acts like a point charge. If you get far enough away from anything, it will act like a point charge. But it's important to actually show these relationships. Okay. And one thing to note about what the field of a ring looks like. So if we plot on the y-axis E of z and z, what we would see is that it will drop off as you get far away and then get bigger as you get closer and then go to 0 at the center, get bigger again, and then drop off. So it drops off 0 in the middle and drops off dramatically as you get further away. All right, so that sums up our ring.